Whoa, welcome to day 155. Hope you're all doing well. These days are weird. It's been a long time just kind of being by yourself or being with your family. Some days are great. Some days not so much. I don't know about you guys. Been kind of tired lately. But life goes on. We make the best of it. So, today, how can I prove that light is a wave? Good look at that. I got a few things for you. I have a demonstration for you with some water. We'll watch a couple of videos together and some activities. So here we go. How many goals for today? There are two. List two facts that prove light is a wave and understanding how frequency and energy and wavelength and how those things relate to electromagnetic waves and visible light waves, which is the part of electromagnetic waves that we can actually sense. That's what we see. So for your warm-up, we've got a couple of questions. If you haven't done those yet, please pause and do them now. Okay. First one is just a note, and that's to know that when you see nm, that means nanometer. Nano is a prefix that means 10 to the minus 9 or 1 billionth. That's 1 divided by 1 billion. So this is what it looks like in scientific notation right here, 1 times 10 to the minus 9 meters. Or in just regular old notation, there are a bunch of zeros there. So that's a nanometer. All right, very small. You're not going to find it on a ruler, and but it's the unit that's used, unit of length that's used to describe the wavelength for lots of waves, including light waves. Okay, next, Roy G. Biv. That's this. This is an acronym that many folks use to remember the order of colors in the rainbow. It's also the order of colors by their wavelength. And so, one example, one end is red, it's 650 nanometers. Violet on the other end is 420 nanometers, so about 2/3 of red's wavelength. So it goes from high wavelength to low wavelength, or high to low. And when you see a rainbow, you're actually seeing light that's coming from the sun, and it's being bent or refracted by the moisture in the air, and it gets bent more or less depending. Sorry, I'm saying that wrong. It gets bent at different angles, and what we end up seeing from that is different colors. So these different colors bend. Sorry, sitting outside getting bit by a bug. These different colors get bent differently. They get refracted differently because of their wavelength. And so when that happens, they separate, and you see a rainbow. The same thing happens with a prism. Okay, let's see. Does the order go from high to low to high, high to low, high to low? And would it make sense for green to be 670 nanometers? Well, no, because that's outside the range. Green is here in the middle, so green must be somewhere between 650 and 420. Green is somewhere in the 500 range. Okay, moving on for today, we're going to go over a little slideshow on electromagnetic waves. And also do a little demo with polarization, and we will take a look at your guided reading from yesterday. All right, so quick little review of your guided reading. A good chunk of this is historical, and there are some pretty neat historical experiments in how we learned about light and how we learned that light behaves like a wave. Light also behaves like a particle. We're going to spend most of the time looking at how light is a wave, but we will also touch on how it behaves like a particle. There were quite a few different experiments. Romer looked at Jupiter's moon, Io, in 1600. We're talking, God, what year is it? I'm talking about 400 years ago with a telescope. that they probably had to hand grind the lens and make it polished and smooth, and and was able to observe the length of time that it took for the moon's shadow to appear and then disappear, and how that changed when we were moving towards versus away, and came up with a pretty good estimate of the speed of light. And even better is this. This is a really cool experiment. Wait for it to load up. Okay, so the Michelson experiment, he measured the distance to a mirror 35 kilometers away. We're talking 25-ish miles. Shined light this from over here. It bounced off the mirror, went this way, bounced back, and then he was able to observe it. And if he's got this spinning at just the right rate, then it would be lined up perfectly to reflect and then reflect again on the other side. If it was spinning too fast or too slow, then the reflections, you can see, they would go somewhere else. Right, they would miss his eyepiece. And so by figuring out how fast this was spinning, and getting that set just right, he could figure out the timing, right? And then that amount of time was the time that took for the light to go from here and back, a total distance of 70 kilometers. So a really cool and pretty simple thing to do back in 1880. So we're talking 140 years ago, that figured out the speed of light, and he was really close. And so that's pretty cool. The other thing that's discussed in here, we're talking about a light year. So a light year is the distance it takes, or the distance light travels in a year, right? And so that's what that concept means. And then polarization, it basically means to put all of the wave energy in one plane. So we're looking at these pictures here, and some of these are in one plane and some are not. Like this one, it's very clear. It's just up and down. It's not going sideways or anything like that. It's just going up, up and down, and up and down, up, down. So this is polarized. This, if we're treating this as two separate waves, if we're treating this as a wave that goes both vertically and horizontally, then it would not be polarized. This, again, just vertical, polarized. This, just horizontal, polarized. This one's doing both. So it's a bit at an angle here, kind of up and to the right. This area here would be down to the left, doing some of both. And so if you've got both waves, then it's not polarized. And a good way to think about polarized is to look at these images here where they have some rope waves traveling through. Whoa, long way to go. Traveling through, here we go, some pallets. So we've got here we've got two pallets, both vertical, and this wave, if you did this with your hand, you could make a wave and a rope, and it would pass through both because they're both lined up vertically. But if you did the same thing here and you went through vertical first, it passes through, but then it tries to pass through a horizontal thing, and the vertical waves, they're going to smack into this and become nothing. A more sciencey example is here. Here we've got two polarizing filters. Sometimes you have these on your sunglasses. Often these are on cameras. Think of a Polaroid camera. That's where the name comes from. It filtered out some of the light for a clearer photo. So these are both lined up vertically, and the wave passes through both. The wave starts off like this, right? Vibrating all over the place. It's got vertical and horizontal components. This thing filters out anything that's not vertical, and vertical is all you get. Here, same thing. We've got components all over the place, vertical, angle, side, horizontal, all over. And the first filter filters out everything that's not vertical. The second filter, though, if you can see, it's oriented horizontally. And so that's going to filter out the vertical stuff, which means there's nothing left. So that, in a nutshell, is polarization, and we'll see some effects of that. And actually, why don't we just go look at that right now? So we just talked about polarization. How does it prove that light is a wave? Well, waves behave. Waves oscillate, right? They go up and down. And so if you can block light with a filter that filters oscillations, right, that only allows them to be vertical or only allows them to be horizontal, then that's proof that light is a wave. So we talked about going through basically posts, and here's a cool little video showing what this ends up looking like. Okay, I think the recording paused there for just a second. Let me back up a little bit. So we've got an image here that's black, and we see that that's some polarized glasses. And notice as he rotates it, the image reappears. All right, so we see we're just looking at a computer screen. He rotates it again, and notice what disappears and what doesn't. All right, still on. You can still see the keys, but you can't see the screen. That tells you something. That tells you that the orientation of the light that's coming out of the screen might be like vertical. So it's all vertical waves that's coming out of the screen, and then the glasses, maybe they filter, the other direction. And so when he lines up the filter and the waves that are coming out of the screen, it's just like the rope going through the posts. Everything shows up. It passes through just fine. But when he rotates it, it starts to get dim and then fully disappears because everything is blocked. That's what it looks like when you use a polarizing filter to block all the light and nothing goes through. Okay, so let's head off to the slideshow for today and go through this. So we see that the big difference with electromagnetic waves versus mechanical waves, electromagnetic waves don't need matter or a medium to transfer the energy. So a lot of the ways that we get information these days, whether it's TV, radio, radio waves is what we use for our cell phones, those things don't require any kind of medium to transfer energy. Think of satellites. They're sending information via energy packets to stations down here on Earth, and there's no matter out in space, or very minimal matter. And so those things, the energy rides on electrical and magnetic fields, and which we'll talk about later, and not on anything that's physical that you can touch. How fast does that stuff go? Well, Nicholson figured out it was 299,000 kilometers per second. We round that to 3 times 10 to the 8th meters per second. If you want that in miles, it's 186,000 miles per second. I believe it's around 47,000 miles around the Earth, so that'd be something like 4 times around the Earth in a second, something like that. If you ever wonder why you see lightning before you hear thunder, lightning is an electromagnetic wave. It travels at the speed of light, or the speed of electromagnetic waves, and so much faster than the speed of sound. The speed of sound is more like 700 miles per hour, not per second, per hour. Way slower. Okay, so where do these waves come from? Well, so they're electromagnetic, and the way you change the electromagnetic fields is by moving something that's charged. So ions are charged particles. Protons and electrons, right? A proton has a positive 1 charge. What's the charge on an electron? Negative 1. All right, so that's what these all have in common. They're all charged, and so when they move, they're moving that charge. And if you've ever moved 2 magnets before, you know that when you move one close to the other, you feel either an attraction or repulsion, right? You move it and the other one moves away. And so that's a magnetic field. And basically what you're doing is you're accelerating one of these things, or actually quite a few of them, and that's causing the field to move. And then when the field moves, it causes something else to move. Action, reaction, right? Or action, reaction. So that's how these waves interact and cause effects. Okay, so if I'm listening to the news on 780 AM, that's 780 kilohertz. If you want to know the wavelength of that, first you have to realize that kilohertz isn't regular hertz, it's thousands of hertz. So this would be 780,000 hertz. That's the frequency. If we want to figure out the wavelength, we just need to use the wave speed equation, which says that the velocity is equal to the frequency times the wavelength. We know the velocity, it's 3 times 10 to the 8th meters per second. And so you could use that number for the velocity, this number 780,000 for the frequency, and then solve for the wavelength. Examples of the electromagnetic spectrum. We're seeing a lot here. I really like this graphic because it does a few things. One, it shows us the visible part and the ranges for those. Keep in mind that the visible spectrum is just this part right here, this tiny little rainbow. The cool thing about this, in addition, is that it gives us an idea of these wavelengths in reference to other things that we've hopefully seen, right? So, like an AM radio wave is the size of a football field. It's huge. It's about 100 meters long. This is why AM radio, you can hear it even when you're on the other side of a mountain or out in the middle of nowhere. The waves are able to bend around things, bend around obstructions. FM radio, not so much. The waves are much shorter. They're closer to 5 meters, 4 meters long. So they sound better, but they're not able to go through obstructions as well. Other waves, microwaves, get a bit smaller, right? A little bit bigger than a baseball. Radar, even smaller, bigger than this period, but smaller than the baseball. Let's see. What else? We've got infrared. So this is a little bit smaller than the size of a cell. The waves that we see are a little bit smaller than the size of a bacteria, and things just get smaller from there. These are all things that you cannot see, right? Like a protein or a water molecule. But what do these things get used for? Well, things that are small are able to penetrate things really well. So we use these smaller waves for stuff like X-rays to get a picture of the inside of your body. Because visible light can't pass through there, but these waves can. And so, anyway, cool graphic. Moving on. Little quiz. Which has the longest wavelength? Radio wave. Which has the highest frequency? It's the one that's the shortest. It's a gamma. That's why they're really dangerous. Give you too much energy in your body, it'll kill you. So compare the wavelength and frequency of a radio wave versus a gamma ray. So just compare and contrast those. Think about how they're similar and how they're different. And the same with infrared and ultraviolet. Think about where those are in comparison to visual light. They bracket visual light. So infrared and ultraviolet are out here, and visual light is in the middle. Okay, so here's some information about different types of waves and again where they are on the spectrum. You can read that at your leisure. A little bit of history. Great video here. Let's take a look at this now.
We saw how our understanding of light has changed over the centuries. In the late 1600s, Huygens proposed that light was a type of wave, while Newton considered it a stream of particles. This debate appeared to be settled in 1801 by Young's double-slit experiment, which showed light passing through two slits produced patterns like water waves. But by 1900, it was clear that light energy was not evenly distributed as expected for a wave. Rather, on the smallest scales, it comes in lumps called quanta or photons. So the question is, how does this affect the double-slit experiment? Here I have a more contained double-slit experiment where there is a laser which fires a beam through a single slit, then through a double slit, and onto a screen where you can see a well-defined interference pattern. There's a series of bright and dark bands, which are much easier to observe than when I use sunlight, because with only one wavelength, there are no other colors involved. This is what a graph of intensity versus position would look like for the interference pattern. What creates that pattern? Consider the bright spot in the middle. The light from each slit has to travel the same distance to reach that point, and hence both waves arrive in phase. That means crests with crests and troughs with troughs.
So we actually do this in class every year. We measure the diameter of your hair, and it's very similar to this, and the same result is what you get. So in this video, you'll look at interference, and he'll also explain how it is that light behaves like a wave, as we see here. But then also later, he's going to show you He's going to set this up here. He's going to set it up using this little machine, and he's going to detect.
Passing through this room, which will also set off the detector. I'm plotting a graph.
He's going to detect single photons being emitted. So, pew, and then another one, pew. He's going to do this for a long time, and you'll see what the results are. It's pretty interesting. All right? A single thing should behave like a particle because it's an individual. It's an individual object, right? It's not a collection of things, and the results are very interesting. So take a look at that. I'll leave the rest for you. You can watch it in high definition. Okay, and so let's look at colors, because colors is a great way to think about the wave portion of light. Why are there different colors? You ever wonder? You ever wonder why a rainbow is different colors, but you look at the sun, it's kind of looks all white. So all the colors are contained, right? When you see white light, you're seeing all of the colors combined as one. And when you see a rainbow, like I said earlier, that's light, white light reflecting or refracting off of water molecules and being bent. And the different colors are bent differently because they have different wavelengths. And so some are able to bend more and others less. And so that acts as a separator. And so that's further proof that light is a wave. Right? If light wasn't a wave, then everything would be refracted at the same rate, but it's not, and so that's what we see. We see differences. So let's take a look here. Which color do you think has more energy? Red or green? Let's look back here. Which of these is going to give more energy? Here we've got an energy boop and another energy boop, and down here we've got boop, 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 boop. Which of those is going to give you more little shocks of energy? Red or green? Well, it turns out the answer is green. It's got a shorter wavelength. The peaks are all the same height. So each of these peaks gives you, say, 1 unit of energy. And here you've got 4 of them, and here you only have 2. So given that everything else is equal, the greater frequency is going to give you more energy because you're getting hit with more waves. Another interesting question, which of these colors has more energy? So white's going to have all the wavelengths, have more energy. Black, none. Another interesting analysis is to think about candles. Since you have some experience with those, would you, if you put your hand near this candle, obviously it's going to feel warm or hot. Candles have different colors. If we look down here, we can see a different color down here versus up here. Which of these is hotter? This is generally yellow. This is blue. And so think about which is hotter, which is colder. And then think about the wavelengths back here and think about where those wavelengths fall and which one has more energy, right? We've got yellow parts and blue parts to this candle. And same with this flame from a gas stove. Which one's got more energy? And then last but not least, so thinking about the wavelengths, which just put them in order. What's got more or less energy? Thinking about wavelength, long and short, and which would be the hottest part. And that's it for the slideshow. There's a little bit of reading back over here on the physics classroom, and there are 3 questions to check your understanding. And that's it. So I hope you enjoy the rest of your day. Hope the quiz goes well, and I will see you tomorrow.